This is Greg Wilson. Greg he got his Ph.D. in 1993 from the University of Edinburgh. And in 1998, he co-founded I guess, what is now a movement called Software Carpentry. Greg's done a number of different things over the years. I remember first discovering Software Carpentry during a 6-hour layover at Oakland Airport when I discovered in the same night XKCD and Software Carpentry. And I only think one of those two things is cool anymore. So I'm really happy to have have Greg here and to introduce him. He's one of the most thoughtful people that I've ever met, and he's also probably the only person that in the same breath can recommend Alinsky's Rules for Radicals and literature on why UML diagrams don't work. So I'm honored to introduce Greg Wilson here today.
Thank you very much. A couple of warnings. First, let's mute this mic because I do have this one on. I pace. Okay, and if I'm coming too close to the edge and not looking down, please let me know. I've only fallen off stage twice and only concussed myself once. But the list of other things I've done while teaching now includes setting fire to a projector, not my fault, and buying a house. I was actually signing the papers on a house purchase a month and a half ago while teaching online, which was a new one for me. So, this one's going to be a little bit speculative. Borrowing a quote from Oscar Wilde, I usually can't tell what I'm thinking until I hear myself say it. So I would really like as much interaction as possible. Please tell me when what I'm saying doesn't make sense or when there's something else that I should be saying or thinking instead, because I'm still exploring these ideas. What I've realized over the last couple of years is that it's really easy to study the things that are out there. It's harder to study the things that aren't. It's harder to look at the things that don't exist. But in many cases, it's actually more fruitful because it'll tell you more about our blind spots and our assumptions. And so what I'd like to do today is explore some things that don't exist and see what they tell us about computing. Right? So let's start about the first thing that didn't exist. I was the first full-time programmer hired by what is now the Edinburgh Parallel Computing Centre. I finished my master's degree. I wanted to stay in Scotland. The physics department had a job for a programmer. I was a programmer. And my job was to take whatever code the scientists had built up over the course of years or decades and make it run a zillion times faster on these funky new parallel machines that we had in the basement. Right? And what I saw over and over again was a lot of people who were much smarter than me stumbling because they lacked basic skills. If you give a supercomputer to the average scientist, it is rather like giving a Formula One race car to the average 16-year-old. Right? And over again, I had people trying to go 300 miles an hour who didn't really know how to shift gears. Near as I can tell, fewer than 15% of scientists have ever used a version control system of any kind. And they've got 100,000 lines of Fortran that they want to parallelize. They have no idea what unit testing is or what unit tests to write, but they want to tell if their code is correct. They don't know how to write a shell script to loop over a set of data files to process each one in turn. Right? So they are doing things manually. And I don't think that we can help them do the bigger stuff until they've got the foundation. So I complained about this. I have enough Scott in my ancestry that complaining is a natural mode. And finally, John Reinders at the Los Alamos National Laboratory said, put up or shut up. I will fill a room with scientists, you come and teach. All right, so Brent and I went and we spent a week teaching, and we thought it was a disaster, and we had stellar ratings from the scientists because it was the first time somebody had said, here are the pieces that are so boring, that work so well, that computer science departments aren't teaching them any longer. Right? The notion of a command shell stopped being interesting from a CS point of view as soon as it started to work. Fair enough, you can't get a research publication by saying, let's do variable expansion on the command line. So it kind of drops out of consciousness. It's just taken for granted. So the first software carpentry class ran in 1998 at Los Alamos National Laboratory, and that was my first exposure to this idea that what isn't there, in this case training in the basics, can tell you a lot about how a field sees itself. Computing in academia is owned intellectually by the people who do exciting stuff that lands on the covers of magazines. That means HPC, that means big data. That means 5 to 15% of researchers. Because the survey that we did with Joe Hannay in 2008-2009, we asked 1,972 scientists, what do you do? And it really is 5 to 15% who have the skills to take advantage of the kinds of facilities that you have here. Turning that over, 85 to 95% can't use what you're offering. Maybe it's because their problems don't need your resources, but more often it's they're just not ready to approach. Open is not the same as accessible. The fact that they could do it is meaningless if they can't do it. While all this was going on, I wound up being the book review editor for Dr. Dobbs' journal, because free books. Right? Books, it's a physical artifact with... Sorry, I had to explain to my niece the other day what it meant to wind a watch, because she'd read the phrase in a Harry Potter book, and she's 29 years old, and she had never seen a watch that you actually wind. Right? What I found was that the books I was getting kept rehashing the same handful of topics, and there were enormous gaps, things that I wanted to know that every programmer I spoke to wanted to know, but when you said, why isn't there a book? They'd go, oh yeah, why isn't there a book? For example, how many of you have ever taken a course on compilers? Okay. Pretty standard senior topic in an undergraduate CS program. There are, last time I checked, 700 books on Amazon still in print on compilers. There are only 3 books that I can find that are about debuggers. None of them are good. And there are no undergraduate classes at any R1 university that I've been able to find on debugging, even though we know that that is where developers spend 40 to 75% of their time. It's as if we were only teaching surgeons brain surgery and ignoring everything below the neck. So why don't those books exist? Why aren't there other books like it on other tools? And I actually tried to conjure these books into being by doing a little bit of sympathetic magic. I started writing reviews of books that didn't exist. You know, if you wash your car, it rains, right? Or I don't know if that's just a Canadian thing, right? And I thought, well, if I write the review, maybe it will inspire somebody to write the book. Maybe it will draw it into being. And we did have a couple of books, but I'm still waiting for a decent book on the construction and use of debuggers. And given the choice, I'd much rather have one on the construction. Building a debugger is much harder than building a compiler. Right? They are very, very difficult tools to engineer. There's a lot of science as well as a lot of art in it, and I really wish somebody would write that stuff down. Then I was asked to teach a course on software architecture at the University of Toronto. 24 books later, out of the 100-odd on Amazon that had software architecture in the title, I had discovered that textbooks would describe why you want to describe an architecture, how to describe an architecture, why it's important to describe an architecture, how to negotiate over descriptions of architecture, in those 24 books that were exactly 8 pages describing the architectures of actual systems. 8 pages spread across 24 books. Okay. So imagine doing a degree in actual architecture where we talk about how to do blueprints, but we don't show you any. Okay. It's ludicrous, and yet there is no course that I can find in the English language at any research university that goes through the architectures of actual systems. And then we are surprised that kids get a bachelor's degree and go to the real world and they don't know how to design software. They've never seen software design as a first-class thing. So I got annoyed. Those people in the audience who know me will know that I get annoyed easily. So we put together a series of books. The first attempt was Beautiful Code, won the Jolt Award in 2008. We went to a bunch of programmers and said, show me the most beautiful piece of software you've ever seen and write 10 pages about it. What makes this beautiful? And at the risk of running over time, I have an anecdote about that. I fired off a bunch of emails to famous programmers. And the first person to reply was Rob Pike, one of the inventors of Unix back in the day, currently at Google. And he said, I've never seen any beautiful software, but if you find some, I'd really, really like you to show it to me. And I'm thinking, bloody hell, if Rob Pike, right? So I forwarded that message to Brian Kernighan, who was another early respondent, who had said, yeah, sure, I'll do this. 2 days later, Brian sent me his chapter, the subject of which is the first regular expression matcher that Rob Pike wrote. I have the feeling I've joined a conversation that's been going on for 50 years, right? What we did with the first 2 volumes was get the principal architects of 50 different open source applications to write a chapter each. Tell me about the architecture of your software. How is it designed? What are the parts? How do they fit together? Why is it like that? Give me the talk that you would give to a new developer joining your team in front of the whiteboard. One of the and there were then follow-on books. An undergrad from Montreal named Tavish Armstrong, who's one of the smartest kids I've ever had the privilege to work with, while he's finishing off his bachelor's degree, edited the performance of open source applications. What do you do to make this code go fast? That's another subject which is almost completely absent from the undergraduate curriculum that we all actually care about. What a great way to teach systems and architecture. This is slow. Where and how can we make it faster? It's not there. Subject I'll return to. And the one that just got released, Mike DiBernardo was the main editor, 500 lines or less. See, the problem with these books is that they rely on a lot of background knowledge. Here, we're getting people to write a web server in less than 500 lines of code. Here's the toy version. Here's the simplified one that has all of the key ideas. Here's a 3D game engine. Here's a SAT solver. Right? Here's a spreadsheet. 500 lines of well-commented code plus some text to explain it so that you can actually get through all of them in a course. You won't be surprised to hear that the people who teach software architecture at universities have almost uniformly ignored the existence of these books. Okay? I'll come back to that one as well. Side note, the most interesting observation out of the first 2 comes from a study that was done by a couple of software engineering profs, Martin Robillard and Nanadovich down in, I believe, San Diego. More than half of these chapters explain architecture by recapitulating history. The only way to understand how the software works today is to tell you how it came to be and the changes that were made over time. That was a completely new observation in the literature, right? And may explain why the notations that people have developed, like UML, are almost uniformly ignored by practitioners. The thing they want to know is, how did we get here? The only way to know why this is the way it is to understand a constraint that we had 10 years ago, and it's just not worth fixing now. Right? None of the notations that we have capture temporal evolution of software systems in any meaningful way. Those of you who wish to be rich, famous, and popular, design a notation that does that. It's much more likely to be adopted by practitioners. And this is one of the reasons why I like going back to the practitioners and say, tell me what you know, so that I, as the researcher, can try to condense it, look for patterns, and give you back something that will help you do that better. I lasted as a professor for 3 years and 4 months, which was 3 years, 3 months, and 29 days longer than I should have. And then I restarted Software Carpentry in 2010. Here's another thing that I find absent, and some of you have heard me rant about this before. Day 1, don't use Word or Excel. They don't play nicely with version control. I mean, you can't put a Word file into Git or Subversion or CVS and do diffs and merges, right? Binary file. Perfectly reasonable request from sane human beings is, well, why doesn't it work? My response is, because version control can't handle binary files. It can't handle these data formats. And their question is, why not? And my answer is, mumble, right? And what's up with the Jupyter Notebook? Gosh, this is embarrassing. Have you ever tried to diff or merge Jupyter Notebooks with their embedded base64 encoded PNG image files? Okay. So here I am telling people, don't use these binary formats because they don't play nicely with version control. And then the very next day I'm saying, but use the Jupyter Notebook, it's really cool. Just don't try using it with version control. The problem with teaching scientists is they tend to be intelligent people who can connect the dots. Gosh, that's awkward, right? And here's the thing. There is no technical reason why we can't diff and merge those formats. Word and Excel are XML trees that have been zipped up, right? We know how to diff trees. We have parsers for those formats. We have GUIs that will display them. LibreOffice can display both. The only reason we haven't done this is something I'm going to come to in about 10 minutes, but there is no technical obstacle. I had an estimate from some of the core devs in the LibreOffice team. 3 developers in 8 months could make diff and merge work for Excel in a way that respects things like this column all uses the same formula. Right? Think about how many millions of people would now be willing to adopt version control if it handles their file formats. Right now, we tell them to climb a cliff. If you want to come up here and use this wonderful thing called version control, you have to throw away all of the tools that you know how to use today. This is a great big raised middle finger to a whole lot of people. And we do it over and over again. You build this and you are providing a ramp, not just to your colleagues in the humanities and biology and everybody else who's using these tools, but to the grant administrators with whom you have to interact when you are doing budgets. Don't you wish that the 3 people in Washington, the 2 in the university, the other 2 in the university, and the other 2 in the university, all of whom have to interact with your budget spreadsheet, could stick it into version control so you weren't mailing around copies Thursday before the grant is due in? Hands up if this would not make your life better. Okay? 2 programmer years and we can build this. Right? And the question is why we haven't. I took a bit of a break in 2011 because I wasted a lot of time in 2010 recording videos and trying to turn Software Carpentry into something MOOC-like, and I'd realized that it wasn't working. How many of you are recording video lectures? Okay. Is there money built into the budget for maintenance of those videos? Okay. So think about this. I'm going to give you money to build a piece of software, but there is no maintenance budget. Here's the money to put up the building, but there is no maintenance budget. Alarm bells should be ringing. What I found was, over and over again, somebody would see a bug 15 minutes into a 20-minute video. You cannot patch a video with less than an hour's effort, and it usually takes longer. In fact, it's usually easier to re-record and re-edit the whole thing than it is to try to patch in place. Right? I wanted to find out if this was just me, so I finally took 8 months and started reading the education literature. And as I said in my talk yesterday, as a species, we know a metric ton about education and learning, almost none of which is on the radar of faculty in higher education. Almost everybody who teaches at the college and university level does what they saw done when they were younger, which is sort of like saying, I've been on a lot of plane flights, so I'm qualified to be a pilot. We can get improvements of greater than a full standard deviation with some fairly low-cost changes to teaching practices. And there's a nice little book that's just come out called Small Teaching, which is about the things that you can do with very little investment of effort that research shows will have a positive impact. It's 200 pages long. It'll take you 1 trip to Chicago to read. Okay? And all of these things are evidence-backed. How come I didn't know about this? Right? For example, how many of you use peer instruction? A couple of hands go up. We have 20 years and more than 200 peer-reviewed studies of peer instruction to show that it is a more effective technique with equivalent investment of instructor effort. And that caveat is important. There are lots of techniques that give better outcomes if you have infinite resources to invest. And I've seen some of those in action. The US Navy, for example, can spend essentially as much as it wants on training because the cost of failure for them is a ship that goes down. Right? So $1 million per person on training is a lot cheaper than losing a battleship. But you aren't working in that regime. Right? So something like peer instruction consistently outperforms classic lecturing, but none of the major MOOC platforms directly support it. edX announced about 3 weeks ago that they are now supporting peer instruction. Woohoo! And then you go and read their description. It is nothing that anybody who uses peer instruction would recognize as peer instruction. They are borrowing the label and giving you something which is essentially you get to answer multiple choice questions in a different way. I'm kind of annoyed by that, right? There's no technical reason for its absence. 2 years ago, I had a Google Summer of Code student in Poland implement peer instruction using off-the-shelf open source tools. It turns out that WebRTC and 10 weeks of hacking, and you can build something that does peer instruction for a group of up to about a dozen people, and you're an undergrad with a background in mechanical engineering, and this is your first large programming project. Again, anybody who wishes to be rich, famous, and popular, do this. But the question is why it hasn't been done already. Okay? And then there's computer science, which really should, in many cases, be called computer strong opinion. Okay? We know a whole lot about software and how it's built. Nobody has an undergraduate course on empirical methods in software engineering. How do you study software engineering? What do we know based on data? Right? There are terabytes of data now available. Data science is a big thing. Some of you may have heard of this. Right? And yet, even though most researchers under 40 in software engineering are now doing empirical studies, it's completely absent from the undergrad curriculum. The two main textbooks, Pressman and Somerville, don't talk about these methods at all. They present a few results from 20 or 30 years ago, many of which are now suspect. But the techniques, the methods to go out and actually do the science are completely absent from what we're teaching undergrads. And I worked with Andy Orm at O'Reilly, and we put together a book called Making Software, where we got a whole bunch of people to write a chapter on their favorite evidence-based result in software engineering. Right? Uptake among practitioners, like this. Uptake in academia, down here. Okay? And my question is really, why isn't this now a standard part of the curriculum? And I can give you an example. One of my favorite results from this book. After the construction of Windows Vista, a group at Microsoft went and got all of the digital artifacts that Microsoft had collected. They didn't just have all the changes in the version control repository. They had every single test result, the tests and the results. They had all the chat logs. They had all the email. They had who was on which conference calls, what were the seating plans, flights, everything. And they threw it at the machine learning team and said, please find us something that correlates with faults shipped to customers. The key metric inside Microsoft is faults per DLL. How buggy were the components we shipped? One of the things they looked at was whether there's a correlation between the geographic distribution of the team and faults per DLL. If I've got a team that's all in one room, do they do better than a team that's split between Berlin and Boston and Bangalore? The answer is there is no correlation. That idea that you have to co-locate the team is not backed by evidence. What do you think the single strongest correlation was? Anybody want to take a guess? It's not developer experience. Not the size of the team.
Did the developer use the code they produced?
Nope, it's not do you scratch your own itch. Single strongest correlation was how distributed is the team in the company's organization chart. The more dispersed you are, the higher you have to go to find a common ancestor in the org chart, the more bugs you are going to ship. Because the higher you have to go to find somebody who can resolve disputes, the lower a circle of hell you are living in. Think about it. If you've got a cross-functional team and we have to go to the boss's 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 boss to get resolution of some dispute about what are we trying to do and how are we going to do it, they have no idea what the details are. They don't understand the issues. Right? They're working at the budget and politics level. So you're gridlocked. If, on the other hand, everybody in the team reports to the same person, there are fewer bugs in the software. That's an interesting result and completely not predicted before the study came out. Another interesting result, people have come up with a lot of code metrics, ways to measure properties of code. Nobody has ever published a code metric that is better at predicting either development time or faults in shipped software than simply counting the number of lines of code. WC is as good as everything else that has ever been published for determining how good is the software, from which I take away that we don't really know what good is when it comes to software. Okay? Now, there is a small industry out there of companies building code metrics tools. They were unhappy with this result, but the data is all openly available. I really want undergrads to know this stuff, and the question is why they don't already. This is the other one that I covered yesterday. How many of you know Andreas Stefik? If you take one thing away from this talk, I want you to go and find Andreas Stefik and his work. Here's what we're going to do. 6 years ago, Stefik started to design a programming language for the visually impaired. He wants an accessible programming language. If you've ever worked with a blind programmer, it's an amazing and humbling experience, and you realize just how difficult we're making their lives with our choice of notation. Try to read aloud a C program. Okay? So what he did was, okay, I want to see if my language is actually better, so I'm going to do a controlled study. The three things I'm going to use are Perl, which is the first-year teaching language of choice at his college at the time, the language he's designing called Quorum, and then a placebo called Randomo, a language with a randomly designed syntax. We are going to use a random number generator and a table of ASCII tokens to randomly generate mismatched bits of ASCII as the syntax for the language. And then we're going to see how long it takes people with no previous programming experience to learn to recognize correct programs. It's a common syntactic test in learning English as a second language. Guess what? Perl is as hard to learn as a language with a randomly designed syntax. So he published this paper in 2011, and people went to the trouble of looking up the personal email addresses of his grad students to send hate mail. How dare you criticize my language? Right? Okay, I can get that. But the comments we had when we posted a note about this on the Never Work in Theory blog showed the depths of ignorance. You have people who are working in data analytics saying your result isn't statistically significant because your sample size is small. To which Stefik says, yeah, but if you've got a really strong signal, you can get statistical significance with a small population. Here's our data, here's our statistical tests. You can download the data and rerun it. He went back and redid this study in 2014 with much larger N and 3 independent tests of readability. And what he has shown, to my satisfaction, is that the languages in the C family are all as hard to learn as a language with a randomly designed syntax. Python and Ruby are almost a full standard deviation easier for novices to learn. The language that he's designing, Quorum, where every feature is A/B tested before being added to the language, is almost another full standard deviation, again, easier to learn. So if we actually do usability testing on our programming languages, we can buy ourselves about 1.5 standard deviations on the ramp for learning it. And if you think that's not going to have an effect on how many people stick with programming and how many drop out because it's just confusing and hard, think again. This is basic stuff. And he struggles to get his papers published in programming language journals and conferences. The reaction of the programming language community has largely been, la, 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 I can't hear you, because if you're right, I've been wrong all these years. And the question is why major languages don't user test new features. I mean, this would seem like an obvious thing to do. Right? I am still not convinced that all of the effort put into building Python 3 was worthwhile. I have seen no evidence that it actually improves anything over Python 2 for the majority of users. And we spent 8 years making that transition, something like that. I'm looking at people who know more about Python than I do, right? There's now a movement to build a new scientific programming language called Julia, okay? I want somebody to show me evidence that it's actually going to make users' lives better, because in order to get the Julia ecosystem up to where we are now with Python and R and MATLAB is going to be somewhere between 1,000 and 2,000 programmer years of effort, right? That's enormous. And you'd think that scientists building a programming language for scientists would turn around and say, maybe we ought to have some data before we go off and sack 1,000 programmer years. I'm not saying Julia is not better. I accept that it runs faster, but let's face it, for most scientists most of the time, the major factor in time to solution is how long it takes to get the code to work, not how long it takes to get the code to run. So optimizing the 10% which is runtime without improving the 90% which is coding time is a newbie mistake. Right? So why aren't we thinking about it this way? And I apologize, I thought there was a picture of Fluttershy as a mad scientist and I couldn't find it. All right? Now let's talk about the garbage fire known as Twitter. Okay? And I'm told that I should have localized this for an American audience and called it a dumpster fire. Okay? It turns out that harassment is unstoppable. I mean, it's a genuinely hard problem, unless you're the Olympics or the police force or anybody else that can hold Twitter accountable. Any sort of post during the Olympics which used copyrighted material was taken down in less than 2 minutes. Right? And yet, death threats, slander, harassment, we have just come to accept those as normal. And I want you to convince me that $1 billion couldn't solve harassment at least as well as credit card fraud has been solved. Credit card fraud is still an issue, but I'm willing to bet that most of you have a credit card and mostly don't worry about its use. Right? I'm not saying we can make online a welcoming place for everybody. I am saying that I am ashamed of the online environment I am handing on to my 9-year-old daughter. Right? We could and should do better. It's a solvable problem given will. It's the will that's absent. And the question is, why don't we fix this? Similarly, there's no legal obligation in the United States or Canada to audit algorithms for legally actionable bias. There's a startup in Ontario which is a way for landlords to rate potential tenants. They claimed, when I challenged them, that they are in fact auditing their code to make sure that there is no racial bias, but they refused to publish either the results of the audit or even the technique used for the audit. Just trust us was the answer. Sorry, but I don't. And we know from recent studies that there is a lot of bias built into these. Machine learning is essentially, money laundering for bias. It's a way to say, oh, it's not my fault, the computer did that, but the biases are baked in. And the question is why? How many of you have seen the new app Allo? How many of you have seen Bruce Schneier's comments about it? Okay, in order to give you better sentence completion, Google has decided to store everything you ever type into that app forever as plain text, which means that it will always be there for police forces, for government regimes that want to have a look at your communication. There is no end-to-end encryption because it allows them to do line completion. What the hell, right? There, I think it's pretty clear that that decision was made because the people who are building the code have never felt at risk. I'm pretty sure that if you had come from a long list of countries, you would not have made that algorithmic decision. So here's another thing that doesn't exist that I think should, and the question is why not? Here's one more, and then I'll get into summarizing. I'll stop griping and start talking about useful things. How many of you participate in any sort of grassroots learn to code group? Teach kids how to code, after school programs, outreach? Okay. I'm involved with one in Toronto. I helped create one for scientists. And one of the things I realized a couple of years ago after being called out on it publicly was the arrogance that most technical people bring to this. I am here to teach you. The notion that you might have something to teach me is completely absent from the conversation, which isn't really a conversation, it's a lecture. I have JavaScript and CS. I will teach you. There's absolutely no notion that you're going to teach me skills like how to run a meeting and how to organize a community, or what it's like to be disenfranchised, what it's like to be subject to stop and frisk, what it's like to be afraid that no matter what you do, the police officer is going to shoot you, right? All of the conversation that I see tends to be one way. We have technology, we will teach you. Programmers don't realize that there's a whole bunch of other skills that they don't have and that they should be listening. And the question again is why not? Even well-meaning people, the kind of people who will volunteer their time, just don't recognize that organizing a community is a craft that has been honed over a couple of centuries. That there are lots and lots of people who are showing up to these grassroots coding groups who have lots to teach us about everything outside JavaScript, CSS, and HTML. We just don't realize it. So, is there a pattern? Here's the long list of things that I think ought to exist that don't. Is there a pattern to this? I think so. And I think this is the pattern. Number one, gentlemen don't get their hands dirty. And number two, they should be grateful. Okay? Let's take the first one first. How many of you know why tenure exists?
Something at Stanford that the people giving the money objected to the professor.
After the restoration of the monarchy in 1688, Cambridge and Oxford finally pried out of the hands of the church. They became supposedly secular institutions. And now we have a social problem. You see, in Georgian England, employees are by definition not gentlemen. If you are an employee of somebody else, you are beholden to them. You are not able to make free decisions under your own conscience. So you don't get to vote and you don't get a seat in parliament because you're just going to obey whatever your master tells you. Gentlemen are aristocrats who own land and have independent means. They are doctors and lawyers with independent practices. If a professor is an employee of a university, they're not a gentleman. Come in the side door, cook will get you some chicken, right? You don't get to sit at the high table and drink the port. Tenure was instituted in order to make it clear that professors were gentlemen. It's a century later that the notion of it being there to protect free speech was bolted on by Germans during the Romantic Revolution. Okay? And you can still see this inside the university system. It is very clear at university where the class distinctions are. Right? Tenured faculty are the aristocrats. There is a yeoman class of people who have permanent-ish jobs, and then there's the peasantry. And if you're a student, you are essentially a peasant. We are seeing the class system of Georgian England in the 21st century. Right? Gentlemen don't get their hands dirty. Right? Similarly, they should be grateful. There is this sense, particularly in Silicon Valley, that we're building all this cool stuff, and why aren't you more grateful? Why do you not praise us more? And there's certainly a resentment building in Silicon Valley that is manifesting in all sorts of uncomfortable ways. Peter Thiel comes to mind. Let's just go and fund a stealth lawsuit because I don't like what you're saying about me. Right? The revelations yesterday that the creator of the Oculus Rift is funding white supremacists to smear people on Twitter during this election campaign. How many people have seen that? News broke last night, and he's not even ashamed. And I think it's partly a resentment that they, the peasantry, are not more grateful that we, the aristocracy, are allowing them food. Right? Well, the solutions are obvious. First, let's have students get their hands dirty. Right? Let's have them actually go and build stuff. Number two, let's make Empathy 101 a required course at university. Right? Well, yeah, that's not going to work. Right? The response to the first is they already do a lot of programming. There's not a realization that programming by itself isn't really what I mean by getting your hands dirty. Interacting with other people who have other needs and other perspectives is what I mean, and that's not happening. And teaching empathy, that's really hard. Hard enough that I regard it as unsolvable in the classroom. I can teach you how to give the right responses to questions about medical ethics. I cannot teach you to actually care about medical ethics, right? So, what can we actually achieve? Well, let's analyze a little bit more. Some smart young people get CS degrees. Most never pay attention to computer science again. We've seen this over and over. People go through CS, but once they are out of the classroom, they do not participate in the professional societies, and they do not read the research literature. They pay much less attention to new developments in academia than their counterparts in engineering disciplines or in medicine. Okay? Medical professionals have to keep up with what's being discovered. A mechanical engineer, at least in Canada, has to recertify, so they have to pay some attention to new developments. There is no similar requirement on programmers, and so the first international conference on software engineering, 40-odd years ago, had an almost even balance of academics and practitioners. Today, that same conference is 96% academic, and that 4% at the last but one conference was almost all a group from one particular company in South Korea over on a junket. Right? There's almost a complete divorce between the two communities. And yeah, I know it's not just a problem in computing, but I get to work with people in a whole bunch of different fields, and I think it is actually worse in computing than it is in many other disciplines that are supposed to be building things. Right? Similarly, academics don't respect practitioners' timescales. When I was faculty at University of Toronto, it took me 16 months to persuade the Intellectual Property Office to let me open source a small piece of student code. It had no commercial application. It was just going to be useful to a group downtown in Toronto, but the university just didn't know what to do about this whole open source thing. And funny story about that, the way we eventually got it out was we switched from using the BSD license to using the MIT license. They are legally equivalent, but the people in the IPO had never heard of BSD, but they knew MIT was a name brand school. And if it's good enough for MIT, it's good enough for the University of Toronto. I am not making this up. A lot of my stories aren't true. That's a true story, right? And the other thing is that in computer science, at least, academics genuinely don't seem to care if practitioners can read their work. How many of you publish in open access journals? How many of you put preprints up on archive.org or something like that? The ACM and the IEEE are still fighting a ground war against open access. I tripped over this 3 weeks ago. A major conference in computing education held in Australia proudly announces that the proceedings are going to be open access for 2 weeks, after which they're going to be closed down again. Okay? And this is regarded as a major advance from the ACM. This ain't what the rest of the world means by open access. And I help edit neverworkintheory.org, where we try to blog about interesting research results from empirical studies of software engineering that practitioners might care about. And it's a real struggle to find open access copies. Most of the people in software engineering doing research still don't know if they're allowed to put their preprints up on archive.org or a similar server. In fact, the ACM made a very, very quiet announcement a couple of years ago that, yeah, it's okay if you put it up on your own website or on a preprint server as long as it's non-commercial. Right? Again, this ain't what anybody else means by open access. But at the same time, to be fair, practitioners, and I was one of them, really don't understand that research isn't about writing software. Right? A computer scientist's job is not to build big programs. A computer science professor's job is to advance the science of computing, to learn new things about computing. If some software comes out the side, that's okay, but that's not what they're there for, and it's certainly, absolutely not what they're rewarded for. Computer scientists get penalized for writing good code just like real scientists. The extra effort that you put in to actually build test cases, right? To write a user manual, to make it extensible, nobody gives you credit for that. In fact, you fall behind your colleagues because the effort you're putting into making this stuff usable by the next person is time that they're spending in putting into getting the next result out. When I was at the University of Toronto, only 6 of the 63 tenured faculty in computer science used version control. That's in a computer science department. Because where is the reward for them for adopting better practices? Okay? Well, there's a fix for this. We know how to fix this, and this is proposal number 1. Back in 1747, a Scot named James Lind did the first controlled medical experiment in history. See, the problem there was that the British Navy lost more people to scurvy than it did to enemy action during the Napoleonic Wars, by more than an order of magnitude. 6 weeks at sea, and you expected 25 to 50% fatalities. Right? And he said, okay, the way we stop this with vegetables is that we pickle the vegetables. Can we pickle the sailors? So he took 12 men, put them in pairs. One pair got plain water as a control. He didn't call it that, but that was clearly the idea. One pair got lemon juice. One pair got alcohol. One pair got vitriol, which is a weak solution of sulfuric acid. Sucks to be them. I can't remember what the other 2 pairs got, but it was very clear after a couple of weeks that the ones getting lemon juice were improving and the others were stable or worsening. So he published his results and he was ignored because he was a Scot and a commoner. It wasn't until the experiment was repeated 40 years later by an English gentleman with a double-barreled last name that the Admiralty adopted the use of lime juice on ships. This is where the term limeys comes from the British. And it's one of the reasons why their fleet was able to dominate the oceans. The other continental European nations didn't adopt this practice until 50 or 60 years later. The British fleet could stay at sea longer, and that turned out to be a decisive advantage. The medical profession did their best to ignore this until after the Second World War. It wasn't until the Hill and Dahl study in 1950, where they compared smokers and non-smokers and definitively showed the correlation between smoking and lung cancer, that we really had a result that the medical profession said is strong enough that we have to start treating ourselves like an experimental science. And if you want to do a bit of reading, Lewis Thomas has a lovely little book called The Youngest Science. He lived through that period from 1920 to 1960 when medicine decided it was going to be a science. In 1920, none of the new enrollees in medical school at Harvard had ever done a college-level science course. It wasn't expected or required because medicine is something gentlemen do. Right? By 1960, we're seeing the emergence of you have to have organic chemistry, you have to know a little bit about this, that, and the other. Right? This was one of the pivotal moments. And what it led to was this virtual circuit. Right? Because what we found was, number 1, smoking causes cancer, but number 2, most people would rather fail than change. The head of the British Medical Association, when presented with this result, said, in print, what is true in general is, of course, of no assistance when one is dealing with a particular patient. He simply didn't understand what a large scientific study had to do with him. But he was the last of that generation to do that. What we see now is that doctors have to learn science to get into medicine, so they know what it has to do with them, so they teach it to the next generation. Right? We've institutionalized that. So I want to do this for computer science, and I want you to help me. We know that most undergraduate computer science programs have a course, typically called Software Engineering Practical, where you pretend to work on a project. Here's a waterfall model. You're going to do some design, you're going to do some implementation, you're going to do some testing. We also know that they're lying to us. If you go back and ask them after they've graduated and feel safe, they will say, yeah, we didn't do the things you told us. We wrote it up as if we did because we're juggling this with 5 other courses. We can't follow any sort of respectable workflow because of the time constraints you put us under. We just pull an all-nighter the night before and then go back and retroactively fill in our work logs to make it look like we were working steadily. So let's stop asking them to lie to us, right? Let's teach them to do science instead. Here's my proposal. I want to create an undergraduate, junior or senior level course in software engineering where this is one of the assignments or exam questions. Here's some raw data. Here's 6 software projects. Here's the version control repositories. Determine if long functions and methods are more likely to be buggy than short ones. Okay, what do you have to do in order to answer this question? You need tool use. Right? You need some code inspection tools. You need to build a model. What do you mean by more likely to be buggy? Are we talking in toto or are we talking per line? And what kinds of faults are we talking about? And how are we going to attribute faults back to particular locations in software? This is experimental design. This is what a lot of you have to do when you're doing real science. You have to learn some statistics. What's the right statistical test and what are you going to feed into it? We have to get them to do science. Right? And it encourages them to do stuff so they will actually understand and value our research, so they'll engage with us after they graduate. Something that really depressed me, I'm easily depressed. In an undergraduate program in biology in the province of Ontario in 2010, you had to spend a minimum of 6 hours per week doing lab work in order for your program to be certified. Right? That's 2 afternoon labs per week over the course of 4 years. So by the time you graduate, you've done over 100 experiments. Most computer science students at University of Toronto or University of Waterloo, the top 2 CS schools in Ontario, did exactly 1 experiment in 4 years. And it was almost always done badly. They never get exposed to science, so they don't know how to do it, so they don't know how to value it, and around we go. We can fix that, and now's the right time to do it. We can fit this into the existing curriculum, and it is culturally defensible, right? This is data science for programmers. Data science is a hot thing. The dean approves of data science. I don't know your dean, but your dean approves of data science because they all do right now, right? So to say we are going to put more math into a subject which has traditionally had no math in it, okay, I can defend that at a curriculum committee. To say we're going to teach stats and data science to the computer science undergraduates, I can defend that, right? Anybody wants to help me build this course, come and talk to me afterwards. Right? The time is right, in part because software engineering researchers under 40 are almost all doing empirical studies, and this helps them create the grad students they want. This helps them train up a generation who can then go and do their research. That's pretty cool. Okay, what about empathy? You don't have to read the legend to know what this curve is. Okay? Medical school, law school, physical science, computer science, right? Proportion of graduates who are female versus time. Okay? Honestly, I no longer believe my generation has the will to fix this. And there's been some really interesting work by Elizabeth Petitsis about why so many of the efforts to increase diversity in computing have failed over the years. Here's her current hypothesis, and it is still a hypothesis when she's accumulating data, but it rings true. 3 times in my lifetime, we've seen computer science go through this boom, where it suddenly becomes the hottest topic on campus and everybody wants to enroll, right? What happens during that boom? Computer science departments can't handle the load, so they up the entrance requirements. They require a higher GPA to get in, which undoes all of the work they've been doing to try to diversify, because as you up the GPA, in particular, as you require higher entrance for math, you're once again selecting in favor of white Asian males. And then as things cool off, there's more effort put into diversity and it starts to show a little bit of payoff. We saw a little bit of a spike 5 or 6 years ago, and then you get another boom and somebody decides to raise the entrance requirements, and once again you're selecting for the ultra geeks. And this has happened 3 times, and she thinks that she can document this. Right? This is fixable, but I've seen lots of efforts and I've been part of lots of efforts, and I no longer think we can fix it, but we can raise up a generation that will. So here's my plan. There is a really good physics education program here at this university. How many of you have had any contact with it? Okay, it's really, really good. 20% of people who get undergraduate degrees in math go on to become math teachers in some form or another. There are only 2 programs in the entire United States at the college or university level that are training people to teach computer science, and they are both very small. And what Mark Guzdial and others found was that we're stuck in this vicious circle. The universities aren't creating the teachers who specialize in teaching computing, so the high schools can't offer the classes because they can't get the instructors, and because they're not offering the classes, there's no demand for the teachers, so the universities don't institute the programs. And the Georgia Computes effort foundered on this, and the president's current effort to, create 10,000 high school teachers and teach everyone computing is going to hit the same rock, right? But we can start small. I don't believe you can institute an entire undergrad program right now on how to teach CS, but you could start with a single course, and we have the material for doing that. I would really like to see a school like the University of Illinois, a school that others follow, a school that has a strong tradition of science education, start with one senior level undergrad course in computer science education. What do we actually know about teaching programming? It turns out we know a lot. Some of this material would be general. Ambrose et al.'s book, How Learning Works, from 2010, was a soup to nuts summary of what we knew based on evidence about teaching and learning at that time. It's beautiful secondary literature. I highly recommend it. Mark Guzdial, who leads what I regard as the best computing education research group on the planet down at Georgia Tech, recently published Learned Center Design of Computing Education. How do you design lessons to reach the people where they are? Because if you're not helping them do the things they think are important, they're not going to show up and they're not going to learn if they do. Okay, we know a lot about this. We've replicated a lot of classic results specifically for computing, right? Beth Simon, Leo Porter, and others did a multi-year study at San Diego State, looking at peer instructions in first-year programming classes. It works. The effect is undeniable. Guzdial and Erickson, media-first computing increases retention. More people will remember stuff and more people will stay in the program. That's a repeatable result. We've got this stuff we can teach, right? And if you want to know how come attempts to reform teaching haven't worked, Green's book, Building a Better Teacher, is a really good analysis of why attempts at educational reform have failed over the last 30 years in the United States, Canada, Australia, and the United Kingdom. The answer is we're trying to fix the wrong thing. Ironically, the solution was invented in Michigan in the 60s and 70s, ignored here, but adopted in some East Asian countries like Japan and South Korea, and also adopted in Finland sort of by accident. Right? So these are all really good books. We have the raw material, and I have to think that an undergrad course on how to teach programming would be really good at creating the teachers our schools need, but while we're waiting for the schools to create the jobs, people who've learned this could go off and contribute to those grassroots programming groups and help them be more effective. We don't have to wait for school boards. Most kids who've had programming experience before they reach university have had it outside traditional schools. And by most, I mean 80 to 90%. If they got programming, they got it outside the classroom. So that's our channel, and we can create people who will volunteer and do that. Right? And it'll also create the students we wish we had. How many of you teach a first-year physics course? How many of you teach a first-year math course? Okay. Suppose you're teaching first-year math. You want to teach calculus or linear algebra, maybe statistics. That's the classic first-year subject, right? It would be difficult to do if the students you had never seen arithmetic or algebra before. But that's the situation we're in with computing classes. Most of the first-year intake have never programmed, right? Wouldn't it be great if they had? We could do so much more and get so much further. And I'm afraid I'm running over time, aren't I? Yep. So, there's lots more. I'm not going to go into these in detail. I have lots of other, I would really like to fill this hole and fill this void. If anybody wants to talk to me about any of these, please come up afterwards. All of these are things we could build now that I think would be adopted, that fill needs, and their absence tells us something about our blind spots. We can build a better computing profession by filling these in. But honestly, given the events of the last few days and the last few months, I care about this stuff, but I would really rather we were working on stuff that's important. Because compared to this, everything I've been talking about doesn't matter. I made these slides on Tuesday, and sadly, as I think you all know, this slide is now already out of date. So if you do have time to work on something, maybe improving programming education isn't where your time should go. So, thank you all very much. I'd be happy to take questions. We have microphones here. Please, Gabby.
Thanks. I enjoyed the talk, and I think there's a lot of things there that are going to be interesting to talk about. I just wondered if you know what we do here at NCSA, and wonder if you have any ideas about programs we could start or conversations we could start that would move forward in some of these areas.
Yes. Okay. So, how many of your staff am I allowed to steal? Okay. Excellent. 100 broken programs. Okay. I want 100 examples of, here's a couple of pages of code, it's broken, here's how I fix it. Developers spend most of their time debugging, and the main reason people give up on programming is they don't know how to fix what's broken in front of them, because we never teach it as a first-class skill. Okay? We can assemble this, right? I don't think I can teach general principles, because I don't think we have a grand unified theory of debugging, but I can teach by example in the same way that we teach GUI construction by showing you this is bad, here's how to fix it. If you haven't seen Jeff Johnson's book, GUI Bloopers, it is the single best introduction to user interface design I've ever come across, because he says in the intro, I can't teach you how to build a good interface. I can tell you how to fix a bad one. And after you've done that 100 times, you'll stop making those mistakes. So this is something that I think people here at NCSA could dive into right now. And you don't even have to think very hard about the examples that you would personally pick. The other one I would really like to see out of NCSA is close enough for scientific work. And I tried to bootstrap this at the WISPY meeting 2 years ago. We no longer teach unit testing, or testing rather, as part of a usual software carpentry workshop. Katie does, and a couple of other people do. But my experience has been that all we do is frustrate the scientists, because here's how the conversation goes. Here's how to write unit tests. Here's a unit testing framework to rerun them. And they go, excellent, what tests should I write? And I say, I don't know. I'm not a bioinformatician. And they say, well, I don't know either. I'm not a computer scientist. We don't know how to test most of the code that scientists are writing. I don't think we know enough to write a general theory, but what I'd like is lots and lots of little examples. How do you test a simple n-body simulation? Here's a page of code that just integrates Newton's equations, and here's the tests that you would write for that. Show me all of those examples so that I have some idea of what is expected in my field. I mean, there's the joke, it's not particularly original or particularly funny, but physicists worry about decimal places, astronomers worry about the exponent, and economists are happy if they've got the sign right. Okay? There's different expectations in different fields, and it's really hard for grad students to find out what those expectations and methods are. Right? So you've got people who do this all the time. Right? Writing it down so that other people can learn from that, so that you can set the expectations, would be wonderful. There's other things on this list that would be great as well, but those are the two that I think NCSA could just knock off. I don't know who would fund it. Thank you. One over here. All of these slides are online and they're all CC licensed, and I think Matt will probably circulate a link or something like that if people want to dive in. Please.
Thank you. I agree with the not finding debugging books. I've kind of looked for that myself before, and so writing one, I might be crazy enough to do it, but I'm not particularly qualified. However, for some of the books that you have done, it seems like you kind of made the framework, asked other people, and compiled it together. Might that work for someone who's crazy but not qualified?
I think that a book on debuggers is, to be useful, is going to have to be essentially single voice. in the same way that most successful textbooks now are single voice, because you've got to go end to end and explore the whole thing. I think a collection of chapters that sample is good for a graduate level reading course. But if what we're trying to do is teach undergraduates how to build debuggers so that they'll understand how they work and be able to do it, I'm not sure that the chorus model that I've used with the books that I've edited is going to produce what we want. And we're finding this with the software carpentry lessons. If you've got a bunch of little things, you can crowdsource. But the distinguishing feature of a lesson, a good lesson, is that there's a narrative arc that runs through it. And it's difficult to write a novel by committee, right? So I'd be happy to be wrong, but my gut is telling me that's not going to be the right approach for this one. If on the other
I
hand,
guess I better get qualified then.
yeah, yes, please do, right? You'll be rich, famous, and popular, except for the rich bit.
Oh, popular too.
Yeah. Any others? One over here, please.
Well, how about this one? So you were talking about the process of organizing groups of people. And one book that I've admired, and I'm wondering if you think that this sort of thinking is relevant, is the Weinberg's Psychology of Computer Programming, where he's kind of talking about how people need to work together to be effective organizing teams, and about egoless programming and things like that. He's not talking about technical things like version control, but
and it was also, it's also pre-scientific in the sense that it is one person's collection of anecdotes. It's things that worked for me. And increasingly I feel that if you go to successful people and say what works, what you're really saying is what lottery numbers worked for you. Because most of the time, for an individual, success is being in the right place at the right time, rather than what they did, and they can often misattribute it. The book that I have found most helpful about community organization, about getting groups to work together effectively, is Michael Jakoby Brown's Building Powerful Community Organizations. This is a really, really good book. He has spent 40 years working in community organization, right? And the best part about this book, which I completely missed the first time through, was the worksheets. Every few pages he says, here's a couple of questions that you should answer now about who you are, what you're trying to do, who you're trying to help, how you're going to do it. And the first time through, I didn't bother to answer the questions, even though it says right there on the first page in big bold letters, you won't get anything out of this book unless you stop and think and answer the questions. He was right. All right? There's a ton in here about how to get people to figure out what they want and work towards it. It's different from managing them. It's very different from managing them. This is about empowering them and nihil pro nobis sine nobis, nothing for us without us, right? It's not, I'm telling you what to do, please follow me. It's, okay, what are we going to do together and where do we want to get to? And again, this is a perspective that's almost entirely missing in the education that we give undergraduates. And then we wonder why they go out and think that all problems have simple technical solutions. I'm learning a lot by going through this a second time. Highly recommend it. One down here. Just as a footnote to that, do you know Carl Fogle's book, Producing Open Source Software? Okay, so the whole thing is available free online at producingoss.com. Carl is the reason that Subversion and Apache are usable pieces of software. And in the early 2000s, he said every successful open source project does some things more or less the same way, and nobody's written it down. Let me write it down for you. And he's in the process of revising it. It's been delayed by a couple of family issues. It's almost ready to come out. But this is what all successful open source projects have in common, plus or minus. And this is from somebody who hasn't just been involved in one and hasn't just worked for large corporations for his entire life. He's been involved in a diversity of groups. So I think this is more useful now than Weinberg. Not to disparage Weinberg, but he had one point of view. This is pulling together several, right? And it's also, let's face it, in academia, it's really hard to give orders. You mostly have to persuade and shame, right? Please.
You mentioned you had a 9-year-old daughter. Are you teaching her to code, and what are you using?
We started with Scratch. How many of you have used Scratch? Okay, there's 35 years of really solid research and practice behind Scratch. It comes out of the group at MIT that was founded by Seymour Papert. It is a beautiful tool. It doesn't do everything, it doesn't get you all of the way, but as an introduction for little kids, Scratch, and there's now a similar system called Blockly, absolutely that's what you start with. And if anybody builds something like that for non-programmer adults to use to program the PVR or control their fridge or Internet of Things, they will in fact be rich, famous, and popular, and I'm not joking. It makes programming accessible in a way that text-based tools don't. I'm in the process of working with her to teach her a bit of Python. And there is, sorry, I keep doing this to you. It's not coming up in the first few. Okay, so there's a really good book that's not coming up on Amazon right now, which is how you write Minecraft plugins in Python. But it's really teaching you Python by showing you how to do things in Minecraft. Whoever wrote that book is a real software engineer, because I installed the tools on my daughter's laptop, and then we ran the Minecraft server, and it said, I'm sorry, these tools won't work with your current version of Minecraft. You're 2 revs ahead of what these tools are written for. And my first thought was, oh crap. And then the next line comes up and says, go here in Minecraft, click here, and run an alternative server that's downgraded by 2 versions. I do that, and it just works. Hands up those of you who have ever just done a downgrade by selecting from a pull-down box and it just plain worked. Okay. My daughter thinks that's normal. I don't know what to tell her. I'm kind of like, nope, that's not. And the reason I couldn't talk to her last night was that her Windows machine had decided to do 2 hours of mandatory updates. One of these things is not like the other. I'll see if I can find the link and pull it up. It's a really well-written book.
If you search for
plugins?
Minecraft plugins, you'll find it right away. So a tip to the audience members when you're asking questions and making comments, these are being recorded online, and the people online will miss your very valuable insights if you don't have a microphone.
That's not it. No, that's not the one that I promise I will pull it up and I will add it to the slide. Okay? I'm sorry, I think we're over time, right?
I think we are over
Okay,
time. I
apologies.
actually have a copy of that book in my office, so if anybody wants to see it, it's on the 4th floor.
2
but
thumbs
let's
up.
thank Greg again for this great talk.
Thank you.